And today's lecture then will be about, first we will talk about gravitational lensing, at least in the weak field regime that we were discussing last week. And once we're done with that, I'm going to move on to talk about cosmology, the basic assumptions in cosmology, and the Friedman equations, which are the equations that govern the evolution of the universe. But let's start with the topic of gravitational lensing. So you may or may not be aware, but this is one of the classical experimental observations of that turned out to be compatible with general relativity. And even if you consider light as particles in Newtonian mechanics, there's a difference of a factor of 2 when you consider the lensing angle, so to say. So the basic idea is the following. So we have an observer, and I'm going to draw the observer. Let's use blue. So we have an observer here that is looking at an object, which is at some point over here, some point object. And between the observer and the object, we have some distribution of matter. So this matter is going to give rise to some Newtonian, well, some gravitational potential here, phi of x. That's going to be in the background. So this could be anything massive. If we work in the weak field regime, it can't be too massive, or we will get out of the weak field regime. But for example, it could be a dark matter halo of a galaxy or a galaxy cluster. We will see an example of that later on. And the idea is that due to the gravity of this cluster, if you look at the light coming from this object here to the right, the light is going to kind of bend. So this observer is going to see this object in this direction, so as if it was over here, rather than in the direction to where it is. And it could also be the case that the light can take several paths in order to get to this observer. And then this observer will see several images of the same object in different positions. In the weak field limit, we will also have kind of distortions of the background and so on. But this is the topic that we're going to discuss today. How does the weak field, how does gravitational lensing work in the weak field limit? So if we first remind ourselves of what the weak field limit was. So last week we looked at the weak field limit. And we found that the metric in the weak field limit, we could describe it in a certain way, that if we look at the line element, it was given by 1 plus 2 phi dt squared minus 1 minus 2 phi dx squared, where this phi was the gravitational potential, the classical gravitational potential. So if we want to consider how light now moves from over here to the observer, then we're going to have to look at the light-like geodesics in the space-time with this metric. And what we do then is that we write down this Lagrangian that we talked about before. That's essentially 1 plus 2 phi. It's essentially inserting the tangent vector of the light into the metric. So it's 1 plus 2 phi t dot squared minus 1 minus 2 phi x dot squared. And the thing now is that we're going to look for light-like solutions. So for light-like solutions, we would have that L is equal to 0. So this means that if we just look at the 0th order approximation, so for phi's that are much smaller than 1, this would mean that if you just look at all of this, phi is much smaller than 1. So approximately, at least, to the leading order, we will have t dot squared minus x dot squared equal to 0. And that's, of course, just a statement that if we don't look really at the perturbation, the speed of light is going to be 1. So this will tell us that that the absolute value of x dot is approximately, well, this should be approximately 0. It's approximately equal to t dot. And furthermore, if we look at this Lagrangian, we see that there is nothing that is explicitly dependent on the parameter t. So that then corresponds to a conserved quantity. So no explicit t dependence. So that tells us that 1 plus 2 phi t dot, because this is the t dot derivative of the Lagrangian, this should be constant. And again, since phi is much smaller, we can arbitrarily set this constant to 1. We can arbitrarily choose the constant to be 1, but since phi here is much smaller than 1, this will mean that t dot is essentially equal to 1, which is just a choice of the relationship between t and the affine parameter of the geodesic that we're going to look for. Essentially, we find that we can use the time essentially as the affine parameter, at least to leading order. So that essentially solves the t Euler Lagrange equation. So what we have left to solve now, or left to look at, is the Euler Lagrange equations in the x direction. So Euler Lagrange equations in x direction. And if we do all of this, what we're going to end up with is something like this: minus the second derivative of x plus 2 x dot nabla phi. This should be equal to t dot squared plus x dot squared times the gradient of phi. So that's if you do the Euler Lagrange variation, you end up with this equation. Now again, we can make some simplifications here and some approximations. So first of all, if we just consider the kind of path that we're going to look at. So let me do the following. Let us look at paths given by approximately x equal to E1 times t. So this is something moving in the x direction plus some position where the light is at time t equals to 0. if we were in Minkowski space, this would of course be a light-like geodesic. However, what we want to do is that we want to take this geodesic, and then when we perturb the space-time using this potential, we should get something else. But as long as phi is not too large, we should get something that is approximately equal to this. So what we can do is that as long as we have something small, then we're going to expect that that x dot, which is essentially the direction of travel of the light, we expect that this will be given by E1 times 1 plus something that's of the order of the deflection angle squared plus E2 V2 plus E3 V3. So what I have done here is that if I look at the deflection angle here, it's essentially this angle. I'm saying that if the deflection angle is small, then what we should have here is essentially a cosine of the deflection angle, which means that is going to be, if the angle is small, something proportional to the square of the angle. Whereas these two components, the components in the directions orthogonal to the original direction, I'm going to have some components that I don't know about, but I can try to solve for them. So what I'm going to do with this one is that I'm just going to look now in the orthogonal directions, so in the E2 and in the E3 directions. And I'm also going to make the following note, that this is going to be approximately equal to 1. We already have this gradient of phi, which is small, so I'm just going to keep the leading order term in this thing. If I look at the second, on the left-hand side, this thing, well, it's both leading order in phi, and it's also only in the one direction to leading order. Because if you just look at the leading order of this x dot, that's going to be given by this E1. So that's not going to matter because it's only going to have a component in the E1 direction. So for the orthogonal directions, it's not going to matter. So if we look, for example, in the 2 direction, so in the y direction, this is then a differential equation for V2. So it's going to be minus V dot 2 is going to be equal to 2, and then the gradient of phi, the second component of that. And all I've done now is to take the second component of this equation. Sorry, there should be a 2 here, not a 1. Because 1 plus 1 is 2, not 1. So this is now rather simple to integrate, because we just have a time derivative here in the left-hand side. And for the 0th order, we know what this time, how this time derivative relates to the x derivative. So if we make the integration here, what we find is that V2 is minus the integral along this this path, well, the 0th order path that the light travels, and we let it go from t equal to minus infinity to t equal to infinity. Then we're going to get the V2 component once the light has passed this passed infinitely far away from this matter potential. And we just integrate, so we get 2, and then the gradient of phi, the 2 component, let me put the 2 downstairs, it's easier to see, dt. Or even dx, because t is essentially equal to x. So that's along the path, and that we were given before. so along this path. So we then, of course, have to see this gradient of phi is, of course, dependent on the position, but the position in itself is dependent on time in this fashion. Any questions? Okay, so let me just do a short example. It's the deflection of a point source. Now, of course, we know that if we just have a point source, we will have the Schwarzschild metric that at some point you will have a strong gravitational field. But the assumption here is that we are far away from the point source for this not to be a problem here. So we then have our point source. And let's draw now a light. So to first approximation, the light will just go by like that. And that's if we just have the Minkowski spacetime. Of course, what's going to happen in reality is that this light is going to deflect. If I could draw properly, going to deflect off, and we're going to have some deflection angle alpha there. So the question is, what is alpha going to be? Well, let me do everything in the xy plane. So there's going to be no z component. So we know that for the point mass, phi, the gravitational potential, is minus gm divided by r. Which means that if I take the gradient of that, we can compute it, and it's gm over r cube multiplied by the position vector itself. The position vector being taken from the point mass. And I'm also going to introduce now what is called the impact parameter, which is essentially the projection of the distance between the incoming light signal and something parallel to that, which goes through the point mass. What do we have? Our zeroth order approximation here would be that x would be equal to E1 t plus b E2, right? So this would be our zeroth order approximation. So if we insert this into the gradient here, what we get for the second component, so if I take E2 inner product with gradient of phi, I end up with gm over r3 y, which if I insert this expression turns into gm b divided by the square root of t squared plus b squared to the power of 3. So this means that if I look back now on this deflection formula, what I find is that v2, so the component of the light's velocity in the y direction, is going to be minus the integral from minus infinity to infinity 2 times this component of the gradient, so g mb divided by the square root to the power of 3 dt. And if you actually perform this this integral, we find that this is 4 gm divided by b. So this, if we look then at the light velocity coming out here, that's going to be essentially E1 plus minus 4 gm divided by b E2, well, approximately. And this means that if we look at the angle here, the angle alpha, that's going to be given by the tangent of alpha. That's going to be the 2 component divided by the 1 component, which means that we're going to have V2 divided by 1, because the x component is 1, which is just the absolute value of V2. And since it's a small angle, the tangent of the angle is approximately equal to the angle itself, so alpha is approximately equal to the absolute value of V2, which is then 4gm divided by b. So what I wanted to show also was this image. You might have seen this in some. This is the so-called bullet cluster, and it's one of the more striking evidence for the existence of dark matter, and it's essentially been it's essentially like that because of gravitational lensing. So what you can see here is essentially the 2 different colors in the sky. So you have lots of background galaxies and stuff. So this is the collision. This is a cosmic collision. And in pink, so these things, that's essentially the collisions of gas, where most of the ordinary matter of these colliding clusters are. Whereas the purple regions here, that's the mass distribution that you can infer from gravitational lensing of the background. So what you've done essentially is that you look at the background and you look at how the background is lensed, and then you can infer how the potential looks, and therefore how the matter distribution is there. So the thing here is to note is that when you have these 2 colliding things, you have the ordinary matter in the middle, and ordinary matter collides, so it slows down. Whereas dark matter is essentially collisionless, which means that it's just continues on. So this bullet cluster is one of the more striking, or this was one of the first, but this is the most striking type of evidence for dark matter. That when you have the regular matter ending up there, and when you look at the actual mass distribution of non-luminous matter, you end up far off to the sides. So that means that whatever we have here has to be something else than these gases colliding. So essentially this is from gravitational lensing, and this is from X-ray observations. So X-ray observations of colliding gas. If not, let's change the subject to one of the later subjects that we will discuss, in fact, the latest. The last subject we will discuss, and that's cosmology, which is what I will discuss today, and well, for what remains of today, and also for tomorrow, and then the coming lectures we will discuss more freely rather than going through new material. So when we discuss cosmology, we discuss kind of the history and our predictions for how the future of the universe will look like. So if you look at cosmological models, one of the underlying principles that we have is the so-called cosmological principle. And in words, it might be stated that, well, we should not expect to be in a very, very privileged place in the universe. So we should expect that if we had not been here on Earth, we would have been in some other part of the galaxy or some other part of the universe, but things would have looked more or less the same. So the cosmological principle is the assumption that the universe is homogeneous and isotropic. So homogeneous means that it should look the same wherever we are. So it doesn't matter if we are here in this part of the universe, or if we are 15 billion light years off to somewhere else. The universe should still look more or less the same. It should look the same, apart from some local variations. The isotropy part means that it should be looking the same in all different directions. That means that if I look in one direction, or if I look in a different direction, the universe should, well, on the large scale, look exactly the same in those directions. Then, of course, locally we have variations such as galaxies and stuff like that. But if I point to one direction and I see, well, there is kind of this amount of galaxies in that direction, there should be the same amount of galaxies in a different direction. So this boils down mathematically to saying that the spatial part of the universe, is maximally symmetric. And what this in essence means for a three-dimensional space is that there should exist 6 killing fields. And if we remain in Euclidean space, you will recognize those 6 killing fields as the 3 translations and the 3 degrees of freedom in rotations. But the Euclidean space is not the only option here. In fact, there are 3 different options when it comes to maximally symmetric 3-dimensional spaces. And let's go through them one by one. So the first is that we would be living in something that's like a 3-sphere. So it will be a 3-sphere. That is, we could be living up here, or down here, or down here on this sphere. Well, I can only draw a 2-sphere, so you'll have to make do with that. But in principle, if you could move around this sphere, you could essentially circumnavigate it, given enough time. This is maximally symmetric because, I mean, if you look at the 2-dimensional sphere, you have a maximally symmetric 2-dimensional space has the 2 translational directions and 1 rotational direction. So around every point you have these. These are the 3 rotations of a sphere. So the 2-sphere is a maximally symmetric 2 space. The 3-sphere is the 3-dimensional equivalent of that. The second option, well, that's what you're used to, is the typical just 3-dimensional Euclidean space. So a flat Euclidean space. And finally, what you might be less familiar with is something like, well, that in 2 dimensions would appear something like a horse saddle. So you have this kind of structure. I'm not very good at drawing this. But you would have a hyperbolic surface. So this is called a hyperbolic space. Hyperbolic space. And if you look at the metrics of these, so I'm going to use capital sigma now to denote the line element of just the spatial part of the universe. So on the 3-sphere, this would be given by the r squared plus some constant k to the power of -2 sine squared kr d omega squared. So these are essentially polar coordinates on the sphere. So if you look at the image of the 2-sphere here, I have the radius from a chosen point, and I have an angle here. Those 2 coordinates could describe polar coordinates on the sphere with respect to this point. I have an angle at which I start, and I have the radius that I go. Then this would be the metric. On the 2 sphere, I would just have a single angle there. On the 3 sphere, I of course have an entire. I have 2 angles that I have to choose. In the Euclidean space, you are familiar with the polar coordinates. It's just your regular polar coordinates. It's the r squared plus r squared the omega squared. And if you look at the hyperbolic space, the line element would be the same, the r squared, but we would have k to the minus 2, but instead of sign, we would have the hyperbolic sign. But they are all quite similar, and all of them are based on polar coordinates. I mean, these are your spherical polar coordinates or spherical coordinates. These are spherical coordinates on the 3 sphere. These are spherical coordinates on the 3-dimensional hyperbolic space. The only difference is this function, which is in front of the angular part of the polar coordinates. So I'm going to generally, I'm going to call this d sigma squared equal to the r squared plus s squared of r the omega squared, where this function s is either sine kr over k, r, or the hyperbolic sine kr over k. Note that in the limit when k here goes to 0, this metric goes towards that metric, and this metric goes to that metric as well. And we end up with essentially flat Euclidean space. That might either be seen as when we are so close to this point that this sign is small, or that this hyperbolic sign is small, or that we're just not looking at a large enough space. So these are our choices. So all our choices can be summarized as that, where the different choice of the function s. So what we want now from the cosmological principle is that one of these 3 spaces are going to describe our spatial parts. However, how large our space is might depend on some time coordinates. So what we're going to introduce, a time coordinate t, such that our total line element, the s squared, is given by the t squared minus, because that's the temporal part, and then we want to have the spatial part. In general, we want the spatial part to be such that the size might depend on time. So we introduce some function a of t squared, which is called the scale factor, and then multiply that by this spatial metric. So this is called the Robertson-Walker metric. And what it describes is essentially a space-time where you have one time parameter, and it's built up of different simultaneities, where at each time you might have a different size of your space-time, of your space, sorry. So this a here, a of t, is called the scale factor. Because if you look at t equals to t1, say, you have 1 a of t, and that multiplies all the lengths in this spatial surface. At a different time, t2, AOT may be larger, and then all of the distances in the corresponding spatial surface would be larger as well by that factor. That's why it's called the scale factor. I'm also going to introduce a definition of a special type of observer here. And this is called a co-moving observer. And that is an observer that remains at the same spatial coordinates. So the forward velocity of that observer would just be given by dt. It's just moving in the direction of the time coordinate. And let me say also that this time coordinate t, where we have those maximally symmetric spatial slices, are what we usually take to call the time, or the cosmological time, or when we talk about the cosmology. So that kind of defines our simultaneity here. So before the break, we were talking about the Robertson-Walker universe, which is essentially what we have here. There is this metric. We had some maximally symmetric spatial part described by either the three-sphere, the three-dimensional Euclidean space, or the three-dimensional hyperbolic space. And then we had a time coordinate t. Now, I mean, note here that I could have inserted something like some function BOT squared in front here also. But if I did that, I could just make a change of variables such that that function disappeared. I would get a slightly different function AOT here, but it would be the same spacetime. So I can always choose this BOT here to be 1. And then the co-moving observers get this form velocity. What we have not talked about is how does this space-time appear? We spent last week talking about the weak field limit, and we also talked before about Einstein's field equations. So if this Robertson-Walker space-time is going to describe our universe, it better satisfy some sort of Einstein equations. So the rest of this lecture we will spend on discussing that. So what kinds of stuff can we put in to this universe, and how then do we describe that this universe evolves with time? So this is what is called the FLRW universe. So the RW, of course, is Robertson-Walker. The F is Friedmann, and the L is Lemaitre. So the full name is Friedmann-Lemaitre Robertson-Walker universe. So we need to make sure that this Robertson-Walker spacetime, that it somehow satisfies Einstein's field equations. And the first question is, what are we going to put into this universe? What kind of matter or other stuff are we going to put in? And what we're going to assume is the following. We assume that the universe is filled with an ideal fluid. So that means that this T mu nu, the stress energy tensor, it's going to be given by some energy density and some pressure, and then we're going to have the four velocities of this fluid minus p g mu nu. Now, in order to have a solution that does not break isotropy and the homogeneity, we must make sure, first of all, that rho and p, the pressure and the energy density, only depends on the time coordinate t. If they don't, then we have already broken the homogeneity and isotropy of the universe. So rho and p can only be functions of time, the time coordinate. U here must be the four velocity of a co-moving observer, because if it's not, then we have also broken isotropy. Then we would have a preferred frame, which would be the frame, or rather we would have a preferred direction, which would be the direction that this fluid moves in. And we can't have that. So that means that we have the following: rho and p are functions of t only. And u is equal to dt. So it's the four velocity of a co-moving observer, which also means that this fluid is going to be co-moving. It moves along with the co-moving observers. If we have that, then that is compatible with the Robertson-Walker metric that we already wrote down. However, we can also assume something about the equation of state of the fluid. So let's do the following. A quite general assumption is that the pressure is given by some equation of state parameter P multiplied by the energy density rho. So if you remember to back in the larger course, we had a discussion where we said that W equal to 0. This is a matter gas or dust, and W equals to 1/3 as a photon gas, essentially, or relativistic gas. So the first case here, W equals to 0, corresponds to essentially having a cloud of particles spread all over the universe that is not moving very much, and there is no pressure. Whereas if we have a gas of photons or a gas where the particles have a kinetic energy which is much higher than their mass, so they're almost moving at the speed of light, then we have a pressure of 1/3 of the energy density. So that's a quite general assumption. So once we have said now that we insert this ideal fluid into our universe, we can start looking at the Einstein equations. There is an exercise in the lecture notes, which is to essentially compute the Christoffel symbols of the Robertson-Walker universe. I'm not going to do that explicitly, but I will refer a little bit to the result. But the idea here is that we're going to use this form of the stress energy tensor, and we're going to insert that eventually into the Einstein equations. So let me just say one thing about how this fluid is going to behave with respect to time. So behavior of the fluid is going to be important later when we discuss the evolution of the universe. So if we look at the Einstein equation, on the left-hand side, we have the Einstein tensor, and if we compute the divergence of the Einstein tensor, so g mu nu, we will always find that this is equal to 0 if we use the Levi-Civita connection. But that means that also the energy momentum tensor must have a divergence of 0. And if we insert now the energy momentum tensor of this ideal fluid, what will we find? Well, we find the following. So we take nabla mu, t mu nu. That's if we take into account also that these co-moving observers are actually moving along geodesics. It's rather easy to show that. I will not go through it in detail. Then this entire divergence, we're going to be able to write this as u mu u nu, and then d mu p plus rho plus p plus rho u nu nabla mu u mu. Note here that this is not 0 generally, because it would be 0 if this was mu and this was mu, but that's not the case that we have here. We instead have a divergence of the co-moving four velocity field. So that's the terms that come out from the first term, and then we're going to have a third term, which is g mu nu, and then the derivative d mu acting on p. So if we take into account now that the only coordinate that p and rho depends on is the time t, then only the time derivative is going to be relevant here and here. So these are now 4 equations, because nu here is a free index. But if you put nu to any of the spatial indices, well, that is then 0, that is then 0. And since only the 0 element here is relevant, this is 0 also, because there is no mixed time space components here. So all of the spatial equations here are trivially satisfied, and the only remaining equation is the nu equal to 0 equation. And if we put nu equal to 0, what we find is p dot plus rho dot plus p plus rho. Nu was 0, so that's 1. And then we're going to have here gamma. Let's see what it becomes. Gamma mu 0 minus g0 0, which is 1, and then just p dot. And this should be equal to 0. So the p's cancel out, and we are left with something that looks as follows once we consider also that p here was w times rho. And it's that rho dot plus 1 plus w, and then we look at these Christoffel symbols and we perform the sum. What will come out of that is 3 a dot divided by a, the 3 because we have 3 spatial dimensions, and then rho. So this is equal to 0. So this means that we can integrate this, and what is going to come out is that the logarithm of rho is going to be equal to minus 3 1 plus w multiplied by the logarithm of the scale factor a plus a constant. It's a constant of integration. Or equivalently, if we solve for rho, we find that rho is proportional to the scale factor to the power a to the minus 3, 1 plus w. So as the universe, if the scale factor grows, then the universe expands. And this tells you how the energy density of the fluid changes when the universe expands. So let's just take a quick example of that. If we have a matter gas, which was W equal to 0, what do we find? Well, if we have a matter gas, it's essentially a lot of particles that are not moving in some volume V, and then we let this volume expand. So we take this and we expand it by some scale factor. So this is a cube multiplied by V is the new volume of that. Then we would expect that since all of the energy is located in the dust particles, we would have the same energy, but now in a volume which is a factor a to the cube larger. And that's exactly what we see here, because the energy density now is proportional to a to the minus 3. So if we expand by a factor a lengths, volume expands to the cube, which means that energy density goes as a to the minus 3. A similar argument for the photon gas, we will get a to the minus 4. So it's the same argument, but the fact that photons also go into redshift when the universe expands. That is going to give an extra factor of the scale factor. Are there any questions? Okay. So that about how the fluid itself behaves. Let's look at if we can find what the Einstein equations tells us about the expansion of this universe. So let me just say one quick thing, and that's that the Einstein field equations, they can also, I mean, you're used to them having like the Ricci tensor minus 1/2 g mu nu, the Ricci scalar equals to the to this 8 pi g times the stress energy tensor. But we can rewrite this as just the Ricci tensor has to be equal to 8 pi g times t mu nu minus 1/2 g mu nu t, where t here, that's the trace of the energy momentum tensor. And you can derive that essentially by taking the trace of the Einstein field equations, and that will give you an expression for the Ricci scalar in terms of this t, which you can then move to the other side. But we can rewrite the Einstein field equations in this form. So for the Robertson-Walker universe, we can compute the Ricci tensor here, and then we can compare it to the right-hand side, which we get by inserting this ideal fluid. So R00, so the time components of the Ricci tensor, if you go on and compute it, and the computation is in the lecture notes, you'll get minus 3 second derivative of the scale factor divided by a. You can do the same for the RR component of the Ricci tensor, which will give you something else. It will give you 2a dot squared plus a double dot minus 2 the second derivative of this function that depended on whether I had a flat or a sphere or a hyperbolic space, divided by S itself. Now, when we look at the Einstein field equations, thanks to the spatial symmetries, we're going to get the same resulting equations from the other spatial coordinates as if we were looking at the RR element. So the full set of Einstein field equations are going to be described by the 0,0 component and the RR component. So once we use that, and we use this form of the Einstein equations, well, we can compute now what this is. It's just about inserting our expression for the ideal fluid into T. We have the left-hand side, and we can compute the right-hand side. So if we do that, we arrive at what is called the Friedmann equations. The Friedmann equations, which is in the RTT, that has to be 8 pi g, and then we have the 0,0 component here. I used 0,0 before, so let's continue to use 0,0 minus, and then if I compute the trace and everything, we get rho minus 3p divided by 2 g00. And if we compute that, we will find that it's 4 pi g rho plus 3p. And that then has to be equal to what we computed up here. So it's equal to minus 3 a double dot a. So this is one of the so-called Friedmann equations that results from inserting this ideal fluid and the Robertson-Walker spacetime into the Einstein equations. Now, for the RRR, we can similarly find that this is 4 pi g a squared rho minus p. Again, the entire computation is in the lecture notes. And this should then be equal to what we had up here. So 2a dot squared plus a double dot minus 2 s double prime divided by s. So while I take this to be one of the Friedmann equations, I can solve here for a double dot and insert that here, and I will get the other Friedmann equation, and that is at h squared, which is the so-called Hubble parameter, which I define as a dot divided by a. So it's the rate of change in the scale factor, essentially, squared. That has to be equal to 8 pi g divided by 3 times rho plus the second derivative of s divided by s a squared. So h here is the Hubble parameter. Just to note very quickly here is that we had these different choices of the sphere, the three sphere, the Euclidean space, and the hyperbolic space. So in the three sphere, we would have S would be 1 over k sine kr, which would give you S double prime divided by S equal to minus k squared. For the Euclidean case, we had S equal to R, which gives you S double prime divided by S equal to 0. And finally, for the hyperbolic space, we had S equal to 1 over k hyperbolic sine kr, which gives you S double prime divided by S equal to k squared. So in all of the cases, we can write S double prime divided by S. We can define this to be minus kappa. And using this kappa, we can describe this last Friedmann equation by just replacing here S double prime divided by S by kappa. And in that way, we describe either of those three cases. There were a few more things I wanted to discuss. We have 15 minutes left. So it doesn't really matter too much if we don't manage to discuss everything, because I think we have ample time towards the end of the course to catch up. But the first thing I wanted to connect to was what we had before. Sorry, what this question that was asked, and that was about this apparent singularity when the scale factor goes to 0. So this is where you have probably heard this, the Big Bang. So this is where it comes from. So if we look at this acceleration equation, which we had here, it was telling us the following. It was telling us that A double dot divided by A was proportional to minus rho plus 3p, right? Now, if we now assume, or rather an observation, let me draw a diagram here. So we have an observation that if we look, so if we put time on the x-axis and the scale factor on the y-axis, we are going to be somewhere around here. So this is our position today. We have some time and we have some scale factor. So this is often called T0. That's today. And we can also look and we see that the Hubble parameter is such that it's positive, which means that the universe is expanding today. That means that we know what the derivative is. So we know that A dot is larger than 0 today. However, if we look at this expression and we look at the right-hand side, we see that unless P is smaller than minus rho over 3, then A double dot is smaller than 0. That means that we're going to have generally something that curves down. So if I just extend this by linearity, if I would extend this linearly, so if A double dot would be 0, I would be along that curve. However, I know that A double dot is smaller than 0. And that means that at an earlier time, the A dot must have been smaller. It must have been larger, which means that we get something like this. And that's true for any time. So the only like histories that we can have are histories like this, that at some time in the past are going to cross A equal to 0. Because, of course, if you extend this line far enough, eventually you end up at A equal to 0. So if you just take this at face value and extend the history of the universe backwards in time, then there was a time when A of t was equal to 0. And of course, if you look at the Robertson-Walker spacetime, that's a singularity of this metric. Now, whether that singularity is a true singularity or not depends a little bit, but in many cases, it will be a true singularity. So it essentially means that the universe started out much smaller than it was today and expanded. And we can draw this conclusion based on essentially two things are necessary. It's necessary that this is not fulfilled. So, but I mean, this is a rather strange condition, right? If P is less than minus rho over 3, P must be negative. And if we looked at both the matter and the radiation cases, P was either 0 or 1/3. So it's certainly not the case that we can fulfill this for something like a matter-dominated universe or a radiation-dominated universe. So as long as radiation or matter dominates the universe and the universe is accurately described by general relativity, then we will have a singularity in our spacetime at some distant time, which is in the past for all observers. Is this necessarily bad? Well, we don't know that. I mean, just as you have a singularity in the Schwarzschild solution, we have a singularity now in the Friedmann-Lemaitre-Robertson-Walker solution. There are also many ways out of this. For example, and we will see this next time, I think we'll get to next time, we could introduce something way back in time where the universe actually contains something like this. Some component that has a pressure which is negative. It could happen. Or if you go far enough back in time, of course, if you looked at this relationship, this relationship actually, between the energy density and the scale factor, and A goes to 0, well, this all of a sudden grows very fast. So the universe becomes full of this very, very high energy component, and we don't know a priori that general relativity is going to be valid there. So at some point, we expect quantum gravity to take over. And we currently don't have a good theory of quantum gravity. String theorists may disagree. But I mean, we have no observational evidence for what the theory of quantum gravity is going to be like. So at some point, the regime of validity of general relativity is expected to break down as you come closer to this singularity. So that's kind of what happens in that when you go back in time like this. And again, we will talk next time about inflation, which solves many problems of this kind of Big Bang model, including this, perhaps removing this singularity.